Alright, we're back with part 2 of this alternate approach to u-substitutions. Just a reminder that the alternate approach is going to be fairly similar to the normal approach that's shown in all the other videos from yesterday, but it's going to be identify u, take du dx, then use algebra to isolate dx, and then substitute u and dx back into the original integral. And then from there you have to just use integral properties and integral identities to solve the integral, and then you have to back substitute u, the function of u back in. Alright, so this was our example from the last video. Let's do a few other examples. Alright, so we got this integral of 3e to the x over e to the x plus 2. Alright, so in this case, a couple general guidelines for picking your value of u. Should be the innermost function. So here you've got a function that's just x squared, but then you've got this other function, this other polynomial function inside of an exponential function. So you usually want to pick the inner function. The other one is, the other general rule is if you've got two functions that look like they have equal degrees of sort of nesting, as these two do, you want to pick the more complicated looking one. And so the e to the x plus 2 is the more complicated looking one of the two between the numerator and the denominator. So if we say u equals e to the x plus 2, and then we take du dx equals, well, derivative of e to the x plus 2 with respect to x is just e to the x. Multiply both sides by dx. Divide both sides by e to the x. And then substitute both of these equations, both our equation for dx replaces the dx in the original equation, and our equation for u replaces the u in the original equation. And so what we end up with, or the original integral I should say, what we end up with is that the integral of 3e to the x, again we don't mess with this stuff on top, over, well, the stuff on the bottom is exactly equal to u. And then the dx here is going to be the same thing as all of this stuff. So it's going to be 1 over e to the x du. And a rather nice coincidence, the e to the x's cancel out. We now have a function of x only, which was the whole purpose of u-substitution, regardless of which method you're using. And go back to our properties and integral identities. Well, we can take the constant out, and then we'll have a 1 over x function, which is going to be natural log of absolute value of x plus c. Okay, so pull the 3 out. And then what's left is going to be natural log of the absolute value of u plus c. Alright, and, oh yeah, back substitute. So we get 3 times the natural log of the absolute value of e to the x plus 2 plus c. And that's as far as you can get. Some of you might be tempted to do this. Where that dot is a multiplication symbol, don't do that. Remember, when you multiply, well, actually, one second. Let me pause the video. Alright, yeah, I'm back. You can't actually do this last step because the laws of logarithms which you can find in any Algebra 2 textbook, will tell you that the log of AB is equal to the log of A plus the log of B. So while this might look similar to this, it's not. You have to have the multiplication inside the logarithm. So this don't work. This is about as simple as this function is going to get. All right, two more examples here. Let's take a closer look at this one. Acceleration is negative 75 cosine 5t. This is a type of function called a simple harmonic oscillation. Find v of t if v of 0 is equal to 0. All right, so this is going to require us to get a specific solution since we have one y and x coordinate, or a time and velocity coordinate, for the final function. So we will actually be able to solve that plus c. We're going to have all the fun of a u-substitution mixed in with the fun and joy of solving for a specific solution. So let's go ahead and tackle this. Now, like I said before, your u can sometimes be the innermost function. So we got this 75 here. That's not a whole lot. If we're taking the integral, we can factor that out. But we have a cosine, and then inside of the cosine, we have the 5t. So if we start with this, velocity is the integral of acceleration, and then we substitute our function for acceleration into this. Well, our first step is obvious. We pull the 75 outside. And now the next thing we do is we set u equal to the innermost function, which is 5t. And that means that du dt, remember we don't have x's, we have t's this time, is going to be 5, multiply both sides by t, or not t, dt, and then divide both sides by 5. Okay, take that, substitute it into there, take, give me a new color, here we go, orange. Take that, substitute it in right there, and then the rest of it is pretty routine. Now don't forget, the cosine of u is one function, and the 1/5, that's multiplied by the cosine of u. It's not cosine of u over 5. Some parentheses help to clear that up. All right, 1/5 is a constant. Just because it comes at the end doesn't mean it's any less constant than any other constant. So we can move it outside of the function. So v equals negative 75 times 1/5 times the integral of cosine of u du. All right, we can do two bits of math at the same time here. We can walk and chew gum. All right, so maybe I can't walk and chew gum. All right, so yeah, that's negative 15 times the integral. Oh, whoops, I was supposed to walk and chew gum here. Guess I'm not so good at that. All right, so sorry. We're doing this one step at a time. The educational way. All right. Integral of cosine of u is, in case you forgot, positive sign. Don't forget the plus c. But before we figure out what c is, we got to back substitute our function of u back into this equation. All right, once we've gotten this far, we're done with the definite integral. We've got our, we're done with the indefinite integral. In other words, we have a general solution, but this problem gave us enough information that we can find a specific solution. So what this says is wherever we put in a v, wherever we see a v down here, we put in a 0. Also, what this part here says is wherever we see a t, we put in a 0. So, all right, good news about this is that this inner function comes out to be, or the sine function comes out to be just 0. Sine of anything is 0. And I didn't have to specify whether this is in degrees or radians because sine of 0 radians is the same as sine of 0 degrees or 0 gradians or whatever the heck you want to call it. So all of this means that 0 equals c because all of that became 0. Last but not least, copy your c back into the original function, so we get into the general solution, so we get that v equals negative 15 times the sine of 5t. Okay, that is your specific solution for this for velocity given this acceleration and this initial velocity. Okay, last example is going to be this. If you got if you've got a rational function, one polynomial divided by another, pick the more complicated of the two. So in this case, that's the denominator. And that's going to be our value for u. So u is going to be x squared plus 4, and so du dx is going to be 2x. Again, the 2 comes down, reduce the power by 1. Don't forget, in this step, you're taking a derivative. Seems kind of weird to take a derivative in order to solve an integral, but it works. Alright, this time we will walk and chew gum at the same time. We'll multiply both sides by dx, and we'll divide both sides by 2x. So effectively what we're doing is we're saying dx over 2x, and we're doing the same thing over here, dx over 2x. 2x's cancel out on this side, dx's cancel out on this side, and what we are left with is 1 over 2x times du is equal to dx. Okay, substitute this into the denominator and substitute this in for dx, and then what you're left with is integral of 3x. We didn't substitute anything in for the numerator. 3x over, oops, I think I drew the fraction bar too big there. Okay, yeah, that's just u. The denominator there, that's just u. Times, what the heck was I doing? Oh yeah, 1 over 2x du. And as with all u-substitutions, the x's cancel out. You have to have that, otherwise you don't have a good u-substitution. You got to go all the way back to this step. And what we are then left with is integral of 3 over u times 1/2 du. Rearrange this a little bit. You get 3/2 times the integral of 1 over u du. This is going to be natural log of the absolute value of u. Whoops, no more du, but we do have a plus c. And if I'm going to imitate Sal Khan, I need to back substitute the u into this equation down here. I think my voice dropped an octave too low to be Sal Khan, but anyway. So that's your general solution. You don't have a single point, so you cannot get a specific solution for this, and that's as far as you can go. All right, so those are 4 examples of this alternative way to solve equations that demand u-substitution. Again, it tells you why the dx dx or dt or d whatever your independent variable is shows up when you take the derivative of both sides of your u function, and it also makes some of the sort of preparatory work you have to do to substitute to change the dt back into a du, and makes that a little bit more self-evident. All right, hope this helps. You're welcome to use either approach in my class.